Europe was once home to a wild ape unlike all others. Oreopithecus lived over 7 million years ago, before human evolution had really got underway, yet in many ways it was strangely human. About 7 million years ago, human evolution was just getting started in East Africa. But thousands of kilometers to the north, another ape empire was in its death throes. Europe had been home to several species of apes since about 17 million years ago. Some researchers even think important events in ape evolution happened in Europe. But by 7 million years ago all but one of these apes had vanished. An Italian ape called Oreopithecus was the last species standing from Europe's golden age of apes. Arguably, it was the strangest of the lot. Oreopithecus has been puzzling researchers ever since its discovery in the rocks of Tuscany and Sardinia late in the 19th century. Its fossil bones tell the story of an animal that did not look or act like its European ape ancestors. Instead, Oreopithecus seems to have been oddly like an early member of our human lineage, even though it does not belong on our branch of the ape evolutionary tree. The latest evidence for this comes from an analysis of Oreopithecus's diet. Sherry Nelson at the University of New Mexico in Albuquerque and Lorenzo Rook at the University of Florence, Italy, looked at oxygen and carbon isotopes in the teeth of Oreopithecus. The exact balance of carbon isotopes locked away in fossil teeth can give researchers a sense for the kind of vegetation an extinct animal ate. A low balance, meaning a relatively high level of carbon-12, is typical of vegetation from trees and shrubs. A high balance, with relatively more carbon-13, indicates a diet rich in grasses and sedges. Oreopithecus has been puzzling researchers ever since its discovery. Meanwhile, the oxygen isotopes can reveal the sort of environment in which that vegetation grew. This is because the oxygen isotope balance in teeth reflects the oxygen balance in the dietary vegetation, which in turn is strongly affected by how much water that vegetation routinely lost through evaporation. When both carbon and oxygen ratios are low, it means a closed, wet system, probably forest floor, says Nelson. Where both are high, it means an evaporative system like a grassland. However, the values locked in the Oreopithecus teeth did not fit into either of these categories. The carbon ratios were unusually high but the oxygen ratios were low. This suggests Oreopithecus was unlike almost all apes. Other species, both living and extinct, typically inhabit rainforests and eat the fruits and, to a lesser degree, the foliage that grow in the canopy. Their teeth would record low carbon but high oxygen ratios, because evaporative stress is strong high in the canopy. A later hominin called Paranthropus boisei probably inhabited grasslands near standing water. The high carbon isotope ratios in Oreopithecus's teeth suggest it was eating a diet rich in grasses or sedges. But these plants typically grow in grasslands where there are relatively fewer trees, and no dense canopy to prevent evaporation. So why are the oxygen isotopes in Oreopithecus teeth indicative of a diet rich in vegetation that was not under much evaporative stress? A likely answer is that Oreopithecus had specialized by eating energy-rich underground tubers and corms, or even aquatic vegetation, says Nelson. Neither of these food sources would show much evidence of evaporative stress. This habitat and specialized diet suggests similarities between Oreopithecus and some of the early members of the human branch of the ape tree, the hominins. Like Oreopithecus, early hominins were unusual apes because they lived in more open environments instead of dense rainforests. Ardipithecus, one of the earliest hominins yet discovered, might have lived in or around thin forests that lined riverbanks. There is controversial evidence that Oreopithecus walked upright on two legs. A later hominin called Paranthropus boisei probably inhabited grasslands near standing water. This species is nicknamed Nutcracker Man for its strong jaws and big teeth. But within the last few years scientists have found that P. boisei probably used its tough teeth to chew sedges, particularly energy-rich underground tubers that would have provided the calories needed to support its relatively large brain. In other words, it might have specialized to a life outside dense rainforests in much the same way that Oreopithecus seems to have done. The earliest hominins had to figure out how to find high-quality foods outside of rainforests, says Nelson. Wetlands may have provided important foods for them. It is an intriguing idea, particularly in light of earlier evidence that suggests more parallels between Oreopithecus and the hominins. For instance, some studies indicate that Oreopithecus's hands look superficially like hominin hands, perhaps a sign that it shared our ability to grip objects precisely. Oreopithecus's teeth are also relatively small and hominin-like. Gallons of ink have been spilled discussing why hominins became bipedal. Perhaps most significantly, there is controversial evidence from the skull, the shape of the pelvis and the features of the thigh bones that Oreopithecus walked upright on two legs in the same way that all hominins, including modern humans, do. It is an idea that has been discussed on and off for about 50 years. One of the most recent contributions to the debate, published in 2013 by Gabrielle Russo at Stony Brook University in New York and Liza Shapiro at the University of Texas at Austin, suggested that it is incorrect. The structure of Oreopithecus's spine is inconsistent with two-legged bipedal walking. Oreopithecus was not habitually bipedal, says Russo. Others might still disagree, of course, particularly given what is at stake. Gallons of ink have been spilled discussing why hominins became bipedal. Yet there is still no agreement on what drove such an iconic adaptation, whether it was to give a better view of the environment, make covering long distances more energy efficient, or something else entirely. Europe's last ape might tell us more about Africa's first hominins. In fact, it is not even clear in exactly what sort of environment the shift to bipedalism occurred. If it is someday definitively determined that Oreopithecus was a biped, then it does become interesting to ask what kind of habitat supported its transition from quadruped to biped, says Nelson. In this scenario, studying any commonalities of lifestyle and habitat between Oreopithecus and early hominins might help highlight what drives the evolution of bipedalism, unlocking one of the biggest mysteries in human evolution. We will need to see a lot more research before anything like that can happen. But it is just possible that, one day, Europe's last ape might tell us more about Africa's first hominins.